The question is, are we live? This is the question. Are we live? Okay, I guess we are live. Okay, I guess we are live. So, I prepared about 20 questions from video from the comment. Okay, I guess we are live. And I will go with the first comment that was posted on my video Angle of the Plumb Bob. The comment by Alice Batbar 1. And the person is saying, are you saying the Earth is spinning so fast is what keeps the line Plumb Bob? If the Earth was not spinning, Plumb Bob would be a 45-degree angle. So it's difficult to answer this question because it is not clear what 45-degree angle is measured against. But I can tell you in your comment, but I can tell you this, that if the Earth was not spinning, the line of the Plumb Bob would point directly towards the center of the Earth. If we assume that Earth is made of completely homogeneous material, which is also not exactly the case. However, the Earth is spinning, so the gravity is pulling everything towards the center of the Earth, but there is centrifugal force pulling everything out. And when we sum up these two forces, it ends up that any line of Plumb Bob is not exactly pointing towards the center of the Earth because there is influence of the centrifugal force. And the centrifugal force, for example, is 0 at the north and south pole. So over there, the line of the Plumb Bob would point towards the center of the Earth. And also at the equator, where the centrifugal force is the strongest, but it is also perpendicular to the line of the Earth's rotation. So over there, the line of Plumb Bob would also point towards the center of the Earth. So that was question number 1. Next question is on my video on daily energy budget. And Pussel Mussel 123 says, greetings from a Germany student of geography. I have fortunately discovered your channels 2 weeks ago and have been plowing through your videos and this playlist since. Your videos have proven to be incredibly helpful to understand the topics we discuss in our fundamentals weather and climate class. So structured, so well presented and explained. Thank you. Well, thank you. Keep up the great work. Looking forward to all the topics of fundamentals of weather and climates to come. Well, this is not a question, but I isolated it here because I wanted to tell you, Pussel Mussel 123, as well as all other people, that there is much more to come in the playlist Fundamentals of Weather and Climate. We just started. We barely covered 3 chapters, and there are 20, if I'm not correct chapters to cover. So at least 17 more chapters, and each chapter has 10 to 20, sometimes even more videos. So if you watch all playlists on the fundamentals of weather and climate, I actually believe you will know more than fundamentals. Thank you for your kind words. Okay, we have one comment online. Fan Dorsey says, how do you think advancements in artificial intelligence research will impact atmospheric research, weather prediction? That's a very valid question. Artificial intelligence is extremely hot topic these days, and more researchers are looking into it. I think over time it will become even more important than now. Currently, artificial intelligence is not replacing weather forecast. But what people are using it for is when they get weather forecasts to improve the final product, to train artificial intelligence models against existing databases, to improve the weather forecast that was produced by physics-based models that are solving basic equations, Navier-Stokes equations, thermodynamics equations, and so on. Now, there is research out there in which people use artificial intelligence to directly produce weather forecast, and it did work very well, sometimes even better than these conventional models, but that is still at the level of case studies. And to go from particular case studies, which are maybe sometimes cherry-picked, to go from particular case studies to everyday, day-to-day forecast, it will take some time. I think European Center for Medium-Range Weather Forecasting is running artificial intelligence model these days, but it is still not abandoning the physics-based models. So, in my view, artificial intelligence will only increase in atmospheric sciences and climate predictions. The next question that I isolated here is on my video on the Bernoulli's equation. Jared Stokes 12Q says, why is a raindrop shaped the way it is? Well, we would first have to figure out what do you mean by the way it is, because I don't know what you think the raindrop is shaped like. General popular opinion is that raindrops are shaped like a tear, but that is actually not the case. They are when they are very, very extremely small. In other words, if the raindrop has diameter below about 1 millimeter, then it is indeed shaped the way you say, Jared. It is shaped a little bit like a sphere. But if the diameter of the raindrop increases, then the shape becomes more like a hamburger, becomes more flattened in the direction of falling. And when the raindrop has diameter larger than approximately 3 millimeters, then raindrop becomes like a pancake, pretty much. And that's how it falls through the air. That's because that's because of the following. What is affecting the shape of the raindrop? Well, what is affecting it is strength of gravity, which is pretty much constant, resistance force of the air, which increases with the square of the speed, and surface tension of the droplet. These three forces determine how the droplet will look like, and I just told you how it will look like for different diameters. Also, when the diameter of the drop is below 1 millimeter, we do not call it raindrop, I believe. The next question that came from Eduardog5236 on my video on the Coriolis force demonstration. He says, "Hi doctor, my university has given me green light to do this experiment." He's talking about rotating disk experiment. "What kind of motor did you use for the rotating table? It would really help me to know. Thank you." This is very technical, specific question. I used 12 volt. Well, I mean, I didn't make that rotating table, but the motor is 12 volts, DC, direct current motor. It's brushed motor, so you can easily find it online on Amazon or any other store, and I believe it is not even expensive, probably a few dozens of dollars. The next question is on my video on Maxwell-Boltzmann distribution. Oh, I loved that video. I loved preparing that video, guys. And the comment is from Blue Chemistry 1. He says, "Thank you. All the questions I had about Maxwell's distribution of speed, particularly regarding the mathematical side, you have answered them in this video." Well, thank you very much, Blue Chemistry 1. Again, this is not question, but I isolated it because I also enjoyed making that video so much. Generally, the entire topic of kinetic theory of gases I enjoyed so much. And maybe one of the reasons is because it is not so much covered in atmospheric sciences. In atmospheric sciences, we study atmosphere through Navier-Stokes equations in terms of dynamics. So we look into continuum. And I never delved too much into kinetic theory of gases, and I always wanted, and this was the perfect opportunity. So preparing videos on kinetic theory of gases, I learned so much. It is a fascinating topic. Statistical mechanics, kinetic theory of gases, absolutely great. The next question comes from White Cold Productions, and it's on my video on the saturation vapor pressure. The person says, "Great video, congratulations. Could you tell me what saturation pressure I should consider, ice or water, to calculate absolute humidity, since I have the relative humidity data? I can measure relative humidity using a Testo 6681 sensor. Greetings from UFSC Santa Catarina, Brazil." Greetings to Brazil as well. I hope I visit Brazil one day. So, should you consider saturation pressure with respect to ice or water? Generally, consider it with respect to water. Of course, if the temperature, now this is Brazil, I don't know where you live, where you live in Brazil. Whenever a person says Brazil, I think hot weather. So if the temperatures are above freezing, namely above 0 degrees Celsius, then by all means you have to use saturation pressure over liquid water because the temperatures are positive. But over even for negative temperatures, it is typical to use liquid water, and the difference between saturation pressures for liquid water and ice is small with respect to those calculations that you probably want to do. The difference becomes extremely important in cloud microphysics when we study how liquid droplets and ice grow in clouds. Then this is fundamental. But if you're calculating relative humidity or absolute humidity at the surface for your own home projects, then it doesn't matter. So use liquid water. The next question came from Santosh Nartu 8264, and that's on my video on the gradient wind balance. The person says, "Hello, how the gradient wind and ageostrophic wind are related?" So let's first discuss geostrophic wind. Geostrophic wind is a steady state wind condition that blows when we have equilibrium between the pressure gradient force on one side and the Coriolis force on the other side. So if there is disbalance between these two forces, the wind will not be geostrophic. And what is not geostrophic is called ageostrophic. So we would say actual wind has geostrophic component and ageostrophic component. In ideal case, there is no ageostrophic component because these two forces are in balance. But nothing is ideal in this life, and so the wind as well. And therefore, the component of the wind that is deviating from geostrophic is called ageostrophic. So similarly, gradient wind is balanced between three forces: pressure gradient force, centrifugal force, and Coriolis force. When these three forces are not in balance, then the resulting wind field will have ageostrophic component, because if they are in balance, again we have gradient wind, deviations would be ageostrophic wind. The next question is coming from Sanjivus, and the person is commenting on my video on the Coriolis force demonstration. He says, excellent demonstration. Thanks for the video. The curvature, if the motion changes with respect to reference point, what is the actual motion? Straight line? What happens if you put a wet paintball? Will it draw a straight lines? Okay, I understand. So in that video, I had two cameras. One camera was rotating together with the rotating table, and that is non-inertial reference frame. And another camera was static above the first camera, which is inertial reference frame. And we saw a huge difference in how motion of those small balls, marbles, was observed from these two cameras. In inertial reference frame, those marbles were straight lines. In non-inertial reference frame, they were cycloids. So the person is asking, so which one is it at the end of the day? Well, which one is it is, again, the point of view of the reference system. But he is having good point here. He is saying, but what would happen if we have those wet balls leaving a trail of color? What would happen? Well, what would happen is at the end of the day you would see cycloids. Why would you see cycloids? Because if you look from the point of view of inertial reference frame, indeed those marbles or those wet balls seem to move in the straight line. But from the inertial reference point of view, what is moving is the rotating disc, rotating table underneath. So even if they are going in straight line, the curvature that you would see on the rotating table would not be a straight line, but it would be cycloids that I derived in one of my previous videos and then also demonstrated in the video that you are pointing out here. So excellent question. The next question is on my video on the origin of wind in Navier-Stokes equations. Basitali R6V says, what is the reference for this equation? Can you suggest any book or article? I mean, any book in any book on the atmospheric sciences is excellent. If you want to dwell deep into fluid dynamics of the atmosphere, then of course book by Introduction to Dynamic Meteorology by Holton is an excellent book, but there are many other books like well, now it's slipping my oh yes, another one is, for example, Introduction to Boundary Layer Meteorology by Roland Stoll, and so on. Roya Tadeon online is saying, where is the windiest place on Earth? The windiest place on Earth? That's a good question. I will have to search. I don't know exactly now latitude and longitude of the windiest places on Earth, but one of the windiest places on Earth is for sure Denmark. Wherever we have land next to the ocean, we usually have temperature gradients that are driving local winds. Now, when you also say windiest, do you mean calm winds? Or if you're talking about tornadoes, for example, then the tornado valley in the United States. If you're talking about some local winds, then there are many places around the world that are very, very windy. Antarctica is very windy in terms of katabatic winds. We have another comment online. It says, thank you for answering. What do you think is the biggest misunderstanding the public has about climate change? Climate change. The biggest misunderstanding that the public has about climate change is that riding bicycles will make big difference. That next question comes from Primau Goeng 2058, and it's on my video on wind direction. And the person says 225 degrees. Does the wind coming from southwest and wind going to northeast? So the person is saying basically, is this how the wind blows if we say that the wind direction is 225 degrees? And the person is right. Because in atmospheric sciences, unfortunately, we measure wind on the windrows, and that's measured by the direction from which wind is blowing. I say unfortunately because this is completely opposite to mathematical coordinate systems. So whenever I discussed that in my video on wind direction. Whenever one wants to use meteorological wind direction data in mathematical analysis, there always has to be some massaging of data to transform them into mathematical coordinate system. So in this case, yes, 225, because 0 degrees is north, 90 degrees is east, 180 degrees is south, 270 degrees is west, so 225 degrees is from southwest to northeast. You are right. Another comment online, Roya Tadayon says, how do we see wind? We do not see wind. We cannot see wind. We can sense the wind. We can feel it as it blows across our skin. And we can feel it in the hair and so on, but we cannot see it. We can maybe see it if it picks up some dust. When we have dust storms and other meteorological phenomena like that, then we can see wind. Then another comment comes on my video on quasi-horizontal momentum equation. And the person says, thanks a lot, Professor, for explaining the subject in a simplified way. Can you make videos to describe dynamics as practically used by operational numerical weather prediction models? Dynamics practically applied to numerical weather prediction. Well, all dynamics that I described actually one way or another goes into numerical weather prediction and then numerical weather prediction models. Now, indeed, I understand your comment. For example, what I derived were differential equations, and we cannot insert differential equations into codes and computers. So what we need to do is to put them in finite differences. And how these differential equations were put in final difference form is also a beautiful subject, and I would love to talk about it. And I will talk about it, but it will come later on my channel, because now I have many other things on the plate, like fundamentals of weather and climate, and then I also want to cover thermodynamics in more details, quantitative details, like I covered dynamics. Of course, there are so many more topics in dynamics that I need to cover, but I stopped a little bit because it would be overwhelming just talking about dynamics. So I talk now qualitatively mostly about fundamentals of weather and climate, and at some point I will go back and we will discuss thermodynamics. So stay tuned, it will come later in the future. The next question is on my random walk video, and it's by J. Gordon Leishman 6041. The person says, air is a mixture of different gases, ? Oh dear. I think the person is trying to say that my video is inaccurate and the air is not mixture of gases. Unfortunately, Gordon Leishman 6401, air is mixture of gases. Mixture means it's a chemical substance where when you put together the elements, they keep their chemical properties. That's mixture. And if you watch my video, you will know that in air that I breathe and that you breathe watching me now, there is 78% nitrogen, 21% oxygen, and 1% other gases. And these other gases are mostly argon, and then we go with other water vapor, carbon dioxide, carbon monoxide, and so on. And because air is mixture, all these gases keep their original physical and chemical properties. The next question comes from Zulkar Mainchaugtai, and it's a comment on my video on Rayleigh and Mies scattering. And the person says, amazing as always. Can you please make a video on heat waves? Yes, I can. And that video will come in this playlist on the fundamentals of weather and climate. I think maybe, I'm not sure now, but maybe in the next chapter, which is chapter 4, I am recording this on 4 February 2025, so for reference. I think I will have video on heat waves. So stay tuned, relatively soon there will be video on that. And then Roya Tadayon online says, how can there be clouds in winter when it is too cold for waters to stay a vapor? Well, water is not vapor in clouds. Water in clouds is either either liquid or frozen. And the lower the temperature, the less water air can hold, to say in those layman terms. So when the temperatures are very low, there is very little water that the air can hold, and therefore a lot of it condenses, creating clouds. Now, these clouds in winter are usually not made up of liquid water, but rather of ice. Sometimes they're also made of the so-called supercooled liquid water, and that is liquid water that can be liquid below freezing point. So water stays liquid at negative temperatures in degrees Celsius. The next question that I have here is on my video on Navier-Stokes equations. Rational discourse says, I don't think... Oh, this is a long one. I remember this one. A person is criticizing me. So you see, I put both. I put positive and negative comments. The person has a long comment. It says, I don't think, quotation, what exactly is a parcel of air, end quotation, is really answered by an imaginary volume of air. Isn't that simply replacing the word parcel with the phrase imaginary volume? Could you not equally have chosen to use other words like pocket or particle? The problem is that without further information, such a concept cannot be understood. We know that it is not like the infinitesimal point which can be used to identify the location of a cannonball in flight, where its mass is concentrated at a point in space, because it has to have the properties such as density, pressure, and so on. So what properties does this parcel of air possesses? It definitely has pressure, density, temperature, but what about location, volume, mass? What is the true nature of this velocity u in the Navier-Stokes equations? Wow. Very, very long comment. Well, you answered this question on your own. So parcel of air is a concept that we use in fluid dynamics and atmospheric sciences to represent part of the continuum, we would say. Part of the entire fluid. We do not analyze entire atmosphere. We analyze small volume of the atmosphere, and we call that volume parcel of air. Indeed, I don't know historically why people chose word parcel. They could call it bubble, pocket, whatever you want. Particle. Some people do say particle of air moving somewhere. That's fine, no problem with that. Now, in terms of what property it has, you already answered. It has temperature, pressure, density, volume, surface area, mass, and it has location, coordinates, x, y, and z. And this parcel of air, now depending on the analysis, this is what I can maybe help you with. Depending on the analysis that you are conducting, you don't have to consider all these variables. If you are looking into dynamics and everything is isothermal, then you don't look into temperature that much, because temperature doesn't vary anywhere. The thing is isothermal. But in that case, for example, the wind speed could change with height or with horizontal distance, and then that parcel of air has speed that is different than perhaps the rest of the atmosphere, and that's the concept of parcel of air. Another thing I can say is that we always choose parcel of air to be of the geometry that best suits our analysis. In some cases, it is a cubical parcel of air, like when I derived the pressure gradient force. In other cases, it can be spherical parcel of air, what we typically use in thermodynamics when discussing buoyancy and some thermodynamic processes in the parcel of air. So it's a small volume of air that is used to analyze continuum. The next question comes from Kiava, and the person commented on my video characteristics of the sun. The person says, great video. If the thermonuclear reaction from hydrogen to helium conserves the number of protons and neutrons should be, how is the mass reduced? I thought that all the mass of an atom was concentrated in a proton and neutron, and that each proton neutron had exactly the same mass. Well, this is now quantum physics. You see, the mass comes from the actual mass of the particle, but it also comes from the energy, as we know famous Einstein's equation that E is equal mc squared. So mass and energy are equivalent in the static case, and up to this constant c squared, where c is speed of light, 300,000 kilometers per second. Now, nature favors binding energy compared to the mass. So you see, if you have two protons sitting somewhere apart, then they will only have their static mass, and there is no binding energy because they are not binding to anything. But if you bring them together, then there is bond between them, and part of their mass goes into that bond. In other words, they lose a little bit of mass because now they are together. And nature always favors higher binding energy compared to the rest mass. That is why when the sun burns through thermonuclear reaction, energy is released. Why? Because two hydrogens that are isolated come together to make helium through the process I explained. Two hydrogens, two isolated protons come together, as well as two neutrons come together to make helium. Well, that means four particles are now together and they have binding energy, and nature likes it. And therefore they can release part of their mass in the form of energy that we get on the planet Earth as solar radiation. That is why in quantum physics, when we talk about this, one mass plus another mass, when they are together, is not equal the sum of these two masses. It's always less, because nature, universe, we live in a universe that prefers binding energy over mass energy. Three more questions, if there are no other questions online. So another question is from Super Bhavuk. The person is commenting on my saturation vapor pressure video, and the person says, do you have videos on cloud microphysics as well? Excellent question. Not yet, but I cannot wait to make it. I cannot wait to make it. I have to first cover thermodynamics, and thermodynamics will come together with this fundamentals playlist, but now I'm just publishing videos that you see behind me on the fundamentals of weather and climate. But when I have more time, together with this playlist, I will start recording videos on thermodynamics. And right after thermodynamics, I plan to have videos on cloud microphysics. And the person continues saying, you said towards the end of that you are gonna talk about it, but haven't found any videos regarding that. Please let me know. Cheers. So I just told you it will be sometime in future. I'm recording this on 4 February 2025. I still do not have cloud microphysics videos, but I will have them. So stay tuned. The next question is from Thomas Trapp 4500 on my pressure gradient force video. The person says, I was curious why the pressure in the negative x direction equals the pressure in the positive x direction plus delta P, plus some change in pressure. I am missing something because it just seems oddly specific. Well, in fact, the goal of delta P is not to make it specific. Delta P is any pressure difference. Imagine if you have a cube like this, two sides of the cube. If you say that pressure here is equal pressure here, then there is no pressure difference. And there is no pressure gradient force because there is no pressure gradient. So what one needs to do to demonstrate the existence of the pressure gradient force, to say pressure here is either larger or smaller, but at any rate different than pressure here. And what I said in the video is pressure here is some P, and pressure here is P plus delta P. And delta P can be whatever you want. 1 Pascal, 100 pascals, 1000 pascals, or if you measure in some other units, atmospheres, millibars, whatever you want. So that's the point. It's quite the opposite. This delta P is generic. Two more questions. Thomas 5153 says on my video on temperature layers, what is the range of altitude where air provides the blue sky we see due to Rayleigh scattering? Absolutely great question. Very good question. What is the range of altitude where air provides the blue sky we see due to Rayleigh scattering? So, scattering is most common where air density is largest. Because if the air density is largest, those atoms and molecules that are responsible for scattering are very close together and the light is bouncing off them very strongly. So atmosphere is the most dense in the lowest few kilometers. So most scattering happens in the first approximately 25 kilometers of the atmosphere. And of course, the closer we are to the surface, the more scattering it happens. I also discussed that in my video on the blue sky. I said if you look in the sky and it's blue, and now you look towards the horizon, the sky is always less blue towards the horizon than if you look directly up. That's because towards the horizon you can see long distance away. And you are looking through very dense atmosphere. And that dense atmosphere is scattering so much that the blue light can scatter before reaching your eyes, and what you get is combination of all colors scattering more or less, and it gets white. So atmosphere is always more whitish towards the horizon than if you look directly overhead. And that is also associated with the density of the atmosphere being the largest close to the surface. And okay, so there are 3 questions from Hugo Pilati. Hugo says, "Good evening, teacher. I am a student of civil engineering and in my internship working with structures, I realized that by lack of Fatane, my region will have the highest wind. Knowing this, I would like to study internal pressure on low buildings. In my Brazilian code, I have to utilize the areas on each face of the building. I'm starting to study now, and I would like to know if have another code that use other methods to discover the internal pressures using not just the area of each face." Well, we are now completely switching topics. Internal pressures can be calculated analytically depending on on how many openings you assume that your building has. If you have the so-called uniformly distributed leakages, if you have one dominant opening, like huge window or the door, if you have multiple openings and so on. And that can be calculated. The equation was derived by Professor Barry Vickery, I think, some time ago. And then you can make a code in Python, MATLAB, Fortran, whatever you use, and carry out calculations for your problem in question. Now, I don't know if you mean by code that computer code or you mean Brazilian code. I'm not expert on Brazilian building code, but of course you could use other codes like American code. I live in Canada, Canadian code, Euro code, and so on. And you can compare results from these codes against Brazilian code for your particular case and see how different codes give you results. And the last comment I isolated from my videos is from the person 65 GTO Trips. On my video on the Coriolis force, and particularly my video that Coriolis force does no work. Not does not work, but does no work. It's a force that cannot do work. And that's because Coriolis force always acts perpendicular to the velocity vector. And if something is perpendicular to the velocity vector, it means it cannot accelerate or decelerate, but only in terms of speed, but only change the direction of the motion. And at any rate, that was not the question. The question was, I thought the Earth rotates at a constant velocity. So how can it be considered acceleration? Is an acceleration increase of velocity over time? Stop to increasing over time, or something already moving then increasing velocity? I didn't understand the last sentence, but it's very clear what the person is asking. The person is asking, if the Earth rotates at a constant angular velocity, how is it that it is constantly accelerating? Well, that's because there is misconception sometimes among people that acceleration only means change of speed. Acceleration means change of velocity, and velocity is a vector. Velocity has speed, which is magnitude, and it has direction, which tells you where something is going. Now, when you are in the car and either car accelerates or decelerates, you feel it. You go forward or backwards. And that's indeed acceleration, what people typically think of along the straight line. But when the car is making a turn, you also accelerate in sense that there is centrifugal force pushing you out. So the same is for planet Earth. For example, when planet Earth is rotating, all objects on planet Earth are accelerating towards the center of the Earth. Because if they are not, imagine you and I now watching this video, if we are not pulled towards the center of the Earth, we would be ejected into the outer space. In a way that as the Earth is rotating, we would just continue in a straight line. But we don't continue in a straight line, we stay on the planet Earth. But that's a circular motion, which means there has to be acceleration pushing us towards the center of the Earth. And of course, in the case of planet Earth, that acceleration is caused in the terms of rotation of planet Earth. That acceleration inward is caused by gravity. When Earth is revolving around the sun, again, it is accelerating constantly because there has to be something changing the direction of motion, pushing the Earth towards the sun. And in that case, that acceleration is caused by the gravity of the beautiful sun, and so on. When the car makes the turn, what I discussed, you do not go through the door, but you push on the door and the door pushes back on you, so that means there is normal force of the door pushing you in, thereby providing acceleration so that you do not go through the door, but rather you make that turn together with the car. So to summarize this, acceleration means change of speed, but also it can mean change of direction. And in this particular case, we are talking about change of direction that is causing acceleration. So that is it in terms of the comments that I prepared from my previous videos. I answered 20 questions and I answered several questions from people that are online. Oh, we are 51 minutes online. Let me see how many people. There are 6 people watching. Wow, impressive. Thank you everybody who is watching. I liked this a lot and I will probably do it sometime again. So please send me your questions, post it below videos, and I might select them and answer like this. I will see you in my next video.